In this video, we're going to look at the manual measure capabilities of ColourSpace, which is where measurements can be made of any given display using a probe, either by taking single measurements, continuous measurements, or a sequence of measurements using patches defined either by the sliders or by a set of presets loaded into the system. So before we start, we'll just populate the screen here with a few of our chosen graphs so that we can actually get a feel for what's happening with the different primary colours, the gamma EOTF, differential EOTF and RGB balance, and we'll pop out a patch window. We're going to use a patch window just central here so that you can see everything that's going on. Normally we would be running that full screen with the patch size defined by the settings in the settings menu. So we've got in this case an L32 patch size, a black background color, and we are using a patch scale that is the default 0255 data range because we're using a display that is working in data range rather than video range, but we obviously could set that to video range or super white video or even set it manually, but we're going to go back to our data range. Now at the moment we're targeting Rec 709 and we've got a preset minimum and maximum values both for the profile data, because a black and white patch are set automatically when you start a new profile, as well as the target being set to 0 and 100. Within the manual measure menu we have a zoom widget and a bars widget. The zoom widget shows how far off the colour is compared to the target, which is always the centre, and the bars widget shows the similar information but as RGB or HSL bars, including a luminance bar and a delta E bar. Below that we have some basic information on the target colour space. We have the min and max values for the target colour space, as well as the actual min and max for the profile with the contrast ratio data. We also have the target Y luminance and XY values, and also the actual and then what the error is, either shown as a percentage deviation or as a value deviation. The test patterns opens up a window that gives you access to a number of different test patterns that replace the patch generator. So again, a double click to make them full screen. So here we have a probe alignment test pattern, and then we have contrast and brightness, which are both flashing patterns, so you can see where clipping is occurring either in the highlights with contrast or the lowlights with brightness. And then you have more specialized patterns such as ANSI contrast in two different forms, and we have the more specialized corner box test patterns, which enable you to check for display contrast on displays that have dynamic backlights. So you have corner test pattern 1 and corner test pattern 2. And we'll be adding more images such as black and white ramps and Granger images as time progresses. Setting the test patch colour can be done using the sliders, which here are locked together to give us a grayscale, or via presets, which can be loaded as a CSV list, so something like grayscale large, which gives us 33 patches of grayscale plus red, green and blue primaries. More importantly, the presets can be user defined to match the CMS of any given display, specifically consumer televisions. So for example, the display we're using here has a 10-step grayscale within its internal colour management. So we can use Excel, if we open up an example of this, to generate a simple 10-step patch set, which we have here. So we have 10 steps of grayscale from black to white, plus red, green, blue primaries using a slightly lower than 100% value, which is what we tend to do when we're setting gamut rather than using the full 255 where clipping may occur. But again, that could be any value that you choose. So if we were to load that in, there we have a 10-step grayscale, again with our RGB primaries. And we can now use the patches to directly change the actual patch color, or go back to our slider. If we unlock the slider controls, we can use these to set any alternate patch color. So step in between them, we can move to any particular color we wish in a relatively quick space of time, either through the use of the sliders to select any particular color, either with or without the sliders interlocked, or through the preset patch lists. So if we actually want to take some measurements from a display, either to profile and assess it or for actual calibration work, we can choose the color for the main patch window, connect to our probe, in this case an i1 Display Pro, integration time of 0.75, all in one mode for sync, no extra delay. At the moment, intelligent integration off for a very particular reason, which we will now look into. So with our patch selected, we can now take a measurement, and we will see that the white point as measured is relatively close to target, and this can be seen in all the graphs. So if we zoom into the CIE here, for example, you can see that the measured point compared to the target is slightly off and low, and that is heading towards blue, which we obviously can see when we look at the overall CIE, and is shown in the zoom widget. You can see the cross is slightly off center towards blue, and in the bars widget, where actually it's telling us that it's slightly low in luminance, and as part of that, it is the red low that is making the luminance low. So if we were to raise red slightly on the display's controls, that would cancel out the fact that the display is a little bit too blue. The amount of error we're seeing here is probably below the threshold of most TV controls to correct, but it gives you an idea as to what the graphs themselves do. And now we'll take a measure of black. And you can see that the initial result is all zeros, with a really huge blue cast being shown on the RGB balance. And that's obviously because the probe has failed to read at the black level that this display has with the present integration time that we have set here. But we're going to use intelligent integration, which means that any reading below 0.1 nit will be read multiple times with increasing integration times until two consecutive readings give the same values. And then obviously we know that that is the probe reading accurately. So if we go back and just remeasure black, you can see now we get a set of actual values, and the measured point is fairly consistent with what we'd expect, being a bit blue from target, as shown by the zoom widget. So this shows you that we have the same blue offset, and the RGB bars in chroma only mode show us that we are high luminance because our target luminance is 0, high blue, low green and lower red. Obviously the luminances now needs to be updated to the actual measured values, so we will just go in and click that. And now we can see that our luminance error is 0, but we have a chrominance error. If we turn off chroma only, it shows that actually there's no error. That's because the delta E is so low that the color error is negligible. But obviously we know there is a color error and we do want to see that, so chroma only gives us that option. We can now just run through the patches either with Auto Advance, which will measure each patch in turn using intelligent integration below values of 0.1 nit. The CIE graphs will update as the measurements are made, while the 1D graphs will update at the finish. And then we can see that we have our EOTF, we have our differential EOTF, as well as the RGB balance, and we've got our zoomed in graphs here showing us our actual measured red, green and blue compared to target. We can now use the patch sets to actually look at each measurement in turn, so we can see the error either in the zoom widgets or in the values or in any of the graphs. And every time we click a colour, it will go to that particular patch. And if we want, we can go back to any given patch. So for example, say patch 1, which is the 10% patch here, and say, well, let's remeasure that to see if the original measurement was accurate. We can even step back into the probe options, and although we are reading here a luminance of 0.5 nits, so we are above our intelligent integration threshold, we could either increase that or just increase the integration time, go back and measure, and now it will do a longer integration of the 10% patch, which is not hugely different in this instance. And we can go back and put that back to our usual 0.75 we've been using. More importantly, we can use this using repeat measurements to start to make adjustments using the display's own colour management system. So if we look at, say, the 80% patch, we look at it in standard mode, we can see that there is too high red, too high green, too high blue, because the luminance is out. And obviously we can see that in the target and actual, where the error is predominantly in the luminance with a small error in the X and Y values. But we can use the display's own controls to adjust the colour until we get something more accurate. So if we put this into repeat and measure, we're now going to get continuous updates on the 80% patch. And we can modify the CMS by bringing down red and green and blue until we get what is a much more accurate result. We can see we've still got a bit of a delta E error, and if we zoom right in on the CIE, we can see there's the patch being measured, and you can see obviously that there is some instability either in the display or in the probe. In this case it is in the display, but we can modify that until we get the values as low as possible within the limits of the granularity of the controls of the display. And we can step through each patch in turn, making these adjustments manually, and then run an entire auto advanced sequence through to get a full update of the entire status of the display. If your display has HSL controls, you can obviously set the widget into HSL, and then when you make those changes on the display itself, the two will align. And we also can change the patch controls from RGB into HSL sliders as well.